Gentlemen, as promised, this is a video giving you the rundown on all of our topics. Hopefully we get this done in one take, and you'll see what I mean in a moment. So here is our topics: periodic motion, wave properties, resonance, reflection, interference, refraction, dispersion, visible spectrum, spectroscopy, radiation outside the visible spectrum, music terminology or sound, polarization, Doppler Shift, optical illusions. There's a lot to go through, and let's see if we can get it all done in one shot. We'll start with periodic motion. Periodic motion is quite simply anything that moves back or forth, anything that vibrates, anything that has repetitive motion. A good example is a pendulum. It swings back and forth. One of the things that we like to keep track of for periodic motion is the time it takes. And really we can rephrase that and call it the frequency. They're really the same idea, because period, or the time it takes to complete one cycle, is the same as 1 over frequency, and frequency is the same as 1 over period. Just two ways of saying how often or how frequent does something happen. That brings us into wave properties. We should be pretty familiar with this picture now, but this is a picture of a wave. There are some parts of the wave, like the crest region or the trough region. There are nodes where there's no displacement. There are antinodes with maximum displacement. If we complete one entire cycle, so one full wave, it should have taken us 1 period worth of time, and the wave should be 1 wavelength long. If you put those together, we can talk about the speed of the wave, which is either lambda over period, wavelength over period, or lambda times frequency. If we move on, we get to this idea of resonance. And very simply speaking, resonance just means whenever you match frequencies. If you look at the black and the green line, there's always a crest at the same time, and there's always a trough at the same time. The green line and the black line, or the green wave and the black wave, match frequencies. Their frequencies are the same, so they would resonate. Imagine if the black line represented somebody swinging back and forth, and the line represents how far from the center they are. The green line might represent how much they're being pushed by someone who's trying to keep them going. Now, the red wave, on the other hand, doesn't resonate with either of these. The red wave has a totally different frequency. It doesn't match either of them. If you look at the dotted lines going down, they match up sometimes with the crest, sometimes with the trough, and sometimes in between. So the red wave is not resonating. It's not matching frequencies. Reflection is a very simple idea. When waves hit a surface, they bounce off. If they hit at an angle, they bounce off at an angle. A great example of reflection is using a mirror or listening to an echo. Interference of waves is when two waves collide. If you look at the picture all the way on the left, you have two wave crests coming near each other. When they get towards each other, the wave actually grows. It's like there's one big wave. But this is made up of two smaller pieces that are each still moving different directions. At that one instant of time, though, they come together and they constructively interfere. After that, they go about their ways like nothing happened. If this was a crest and a trough, we would have had destructive interference or canceling of the wave. Because these are both crests, you have constructive interference, or increasing the size of the wave. Next, we move on to refraction. Not only can waves bounce, they can bend. When they go from one material to another, if they're going at an angle, they change direction. At the base, it's because they slow down in different materials and speed up in others. So when I have a wave hit a surface, it's going to slow down. If it's traveling at an angle, it causes it to turn. Since different colors of light travel at different speeds, they also bend differently. So what we have here is two examples of light bending two different ways, going through the same material. Which leads us very nicely into our next topic, dispersion. If you apply this idea of refraction, and you have white light, all those squiggles on the left side, traveling towards a prism, which is just a piece of glass or plastic in a particular shape, you end up having these different colors bend different directions and then spread out. So dispersion is the separation of many colors from white, which is really interference of all the colors together, constructive interference of all the colors. Now, we should probably talk about the visible spectrum and what that is. If we think about all the wavelengths of light, which is represented by this kind of line on the bottom, there's a very teeny tiny region that we can actually see. In that teeny tiny region, there's red light, green light, blue light, all the different colors. Red has a long wavelength, blue has a short wavelength. But we can still only see a few colors, just like we can only hear a few pitches. Our audio range and our visual range is very limited, but that does not mean light doesn't exist outside of this range, or that sound doesn't exist if we can't hear it. Moving on. Spectroscopy takes advantage of this idea. Imagine two different molecules, or an atom and a molecule. Each have their own resonant frequency, or the frequency they like to vibrate at. The first one, on the top, likes to vibrate at the same frequency that green light likes to vibrate. So as white light, the black lines, come into it, only the green light bounces off. That atom acts like a mirror for that green light. The molecule below, it vibrates quicker. It vibrates at the same frequency as blue. So it acts like a mirror that keeps bouncing off blue light. We can use different colors that we see when we look at objects to figure out what atoms are actually in there and what are making them reflect certain colors. So when you look at something through a spectroscope, you don't see a rainbow of colors, you might only see a few bands, one particular shade of green and one particular shade of blue. That might tell you what materials are in it. Back to the spectrum. We just talked about the visible spectrum, the colors we can see, but if we zoom out and look at the whole spectrum, there's a lot of other things that are included. On the short side, light that has very high energy, we have gamma rays. You might think of this as radiation from nuclear sources. You have X-rays that are slightly longer but still go through your body with relative ease, stopping at your bones, of course. Ultraviolet radiation, that's what gives us sunburn. That interacts with our skin in a way that we don't quite like. If you start to get longer than light, we have microwaves. Microwaves are a couple centimeters long and are really convenient for cooking food because they happen to resonate at the same frequency as water molecules. If you go even longer, you have radio waves that can be 20, 30, 40 meters long for a wavelength. But all of this is light. It's all part of the electromagnetic spectrum. There's just a really tiny section of it that we can see. Just like we can only see certain things, we can only hear certain things. Let's think of sound. Sound is really a collection of different waves. On this top picture, you might have three completely different waves, the three different colors. Their frequency, or how often they hit a peak, would represent their pitch. So the blue line is really frequent. It would be a high pitch. Green is less frequent. And red is even less frequent. But if you put those three sounds together, you get a different pattern. The black line represents the interference of these three waves. The sound we hear is very complex. It's a mixture of lots and lots of vibrations all put together. When these vibrations mix together well, we call that consonance, something that sounds good. Here's a picture of consonance. There's two waves that both fit in the same area very well. Because they're about the same size or the same frequency, well, they're not the same same intervals of a frequency, they sound well together. But these two notes that are just slightly off don't fit very well together. So they would not sound good. These might sound dissonant together or sound a little bad. Next we have polarization of light. If you imagine the black dot in the center as a line coming straight towards you and going into your eyes, which quite in fact it is right now, you have light going up and down, left and right, on every axis. On all 360 degrees, light is vibrating. Light is a transverse wave. Now, we can picture that kind of like this line, where black represents the direction of the light, and all these waves go different directions. What a polarizer is basically a gate that only lets things go through in one direction. So the red line that's moving side to side cannot fit through the gate that only allows things going up and down. The blue line that's going on an angle also can't fit through. So what we have afterwards is only straight up and down light. But if I put a second polarizer that goes left and right, no light can get through. Polarizers are very useful in sunglasses and photography to help block out unwanted light, especially light that's already been polarized and aligned in a particular direction after reflecting off of something. Now let's talk about the Doppler shift. Imagine an ambulance that's making sound. Boop, 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 boop. Each of those waves represents a sound coming off of that ambulance. If the ambulance is sitting still, you could picture these waves as circles with the ambulance at the center. Every sound has the ambulance at the center. But if the ambulance were moving, the first wave would center around where the ambulance used to be. And the second wave would center around where the ambulance used to be. The third wave would center around where the ambulance is now. So you end up getting this skewed version of these circles, where the centers don't line up. But what happens here is if you're in front of the ambulance, the sound waves are smushed together, giving it a higher pitch. Whereas the waves behind are lower because they're stretched out. Where really the ambulance is doing something kind of in the center. Last but not least, we have optical illusions. Optical illusions are just pictures or things that we see that don't quite make sense. There's just something about them that tricks us. Now, this can happen a few ways: by fiddling with the way that your brain interprets something, or seeing something that's not quite there, or having your eyes have light that's distorted because of other properties we've talked about. But optical illusions are really always happening. Everything you see is something you interpret. You don't see this video, you see light that's coming out of your screen right now. And it has to travel a decent distance before it gets to your eyes. A lot can happen to light in that time. The sound you hear coming out of my voice is being recreated by your speakers, and it can change on its way to your ear. So I hope what you've taken from this unit, which is quite big with a lot of topics, is that you can't always trust what you see and hear, but if you understand how light and sound work, you can trust it a little bit more. I'll see you guys tomorrow.